So the performance of the BitTorrent network relies heavily on the order in which the pieces are requested by the peers. In this fifth video of the BitTorrent internal series, we take a look at the piece selection algorithm that BitTorrent uses and learn how it makes the network fault tolerant while ensuring a very fast download rate across the network. But before we move forward, I'd like to talk to you about a course on system design that I've been running for over a year now. The course is a cohort-based course, which means I won't be rambling a solution and it will not be a monologue. Instead, a small focused group of 50-60 engineers every cohort will be brainstorming systems and designing it together. This way, we build a solid system and learn from each other's experiences. The course to date is enrolled by 600 plus engineers spanning 9 cohorts and 10 countries. Engineers from companies like Google, Microsoft, GitHub, Slack, Facebook, Tesla, Yelp, Flipkart, Dream11 and many more have taken this course and have some wonderful things to say. The coolest part about the course is the depth we go into and the breadth we cover. We cover topics ranging from real-time text communication for Slack to designing our own toy load balancer to ClickBuzz's live text commentary to doing impressions counting at scale for any advertisement business. In all, we would cover roughly 28 questions and the detailed curriculum split week by week can be found on the course page which is linked in the description down below. So if you are looking to learn system design from the first principles, you will love this course. I have 2 offerings for you. The first one is the live cohort based course which you see on the left side, and the second one is the recorded course which you can see on the right side. The live cohort based course happens every 2 months and it will go on for 8 weeks, while the recorded course contains the recordings from one of the past cohorts as is. If you are in a hurry and want to binge learn system design, I would highly recommend you going for the recorded one. Otherwise, the live cohort is where you can participate and discuss things live with me and the entire cohort and amplify your learnings. The decision is totally up to you. The course details, prerequisites, testimonials can be found on the course page arpitbhayani.me/masterclass, and I would highly recommend you to check that out. I put the link of the course in the description down below. So if you are interested to learn system design, go for it. Check out the link in the description down below, and I hope to see you in my next cohort. Thanks. So the original file that is shared in the network is split into pieces. The length of each piece depends on the torrent that you have, but it would be constant for a particular torrent. Let's say it's 256 KB to 1 MB, right? So every piece, let's say every piece in our torrent is 1 MB big, right? So what would happen is if a file has length of 3 MB and we take a piece size of 1 MB, what would happen? We would have 3 pieces overall. Each of this piece is passed to the hash function which computes a SHA-1 hash of it, and this hash is placed in the .torrent file. Through this, when we are trying to download a particular file, we know that these are the pieces, this is what we want and this is how we can get it, right? So as part of first step, you who would want to download a torrent file, you'll go to the tracker to say, hey, I have this torrent file and I want to download this particular file. So what the tracker would do is it would give you the list of peers in the network. Once you have the list of peers in the network, you'll directly talk to the peers and request for the pieces that you need. And the peer would send you those pieces and then you would concatenate and create the file locally, right? The performance of this entire protocol depends on the order in which pieces are requested. But why? Let me give you a simple example. Let's say I have a file which is 5 MB big, and I'm making a piece of length 1 MB, right? So I'll total have 5 pieces for my entire file, right? So now what would happen is, let's say if everyone starts from piece 0, that everyone requests the piece 0, then piece 1, piece 2, piece 3 and so on and so forth. So what would happen is there might come a state where we know that there would be a seeder in the network who has the entire file, and there would be leechers in the network who are right now downloading the file. And let's say if everyone downloads 0, then 1, then 2, then 3, then 4 and so on and so forth. So for example, after 3 pieces, where everyone in the network has 3 pieces, your seeder left the network. No one has the 4th and the 5th piece. This is where the problem is. You don't want to be in a situation where every peer in the network has the same set of pieces and the seeder left the network. So now your download cannot proceed. So which is where the order in which the pieces are requested by the peers matters a lot, right? So that we don't have an over dependence on the seeder. always. Right. So this is why the order in which we are requesting the pieces matters, and which is why we need a piece selection algorithm with us. Okay. So if we want to devise an algorithm, what would be the core criteria of it? So we would want our piece selection algorithm to fulfill two needs. First, we should be maximizing the download speed of the network. Second, we should be minimizing the dependency on the seeder. We saw the example on why we would want to minimize the dependency on the seeder, because what if the seeder leaves and no one in the network has the piece to complete the download, right? And to maximize the download speed, obviously your piece selection algorithm cannot make the overall download slower, because that's what the aim of a P2P network is, to distribute the file as quickly as possible, right? So that is where we talk about an algorithm called Rarest first piece selection algorithm. By the name, it is self-explanatory that what we are doing is we are trying to go for the rarest piece first. So which means that the piece which is the rarest in the network, we would try to prioritize downloading that. And the piece which are common, we can delay the downloading of that piece. This way, we would be reducing the dependency on the seeder, and we would ensure that everyone in the network has almost all the pieces that are required to complete the file. So that even if seeder leaves the network, you would have enough nodes in the network that would have those pieces so that you can complete the download. Like every node would complete the download. Right? So the core idea of this algorithm is prioritizing downloading of a piece that is rare. So say we have three peers in the network, peer A, peer B and peer C. Peer A wants to download a file. So it would start downloading the pieces from its peer set, B and C. And who gave this peer set? To A, the tracker. So when A joined the network, A talked to the tracker and said, hey, I need peers to download file from. So the tracker would send in B and C, right? So this is how A's peer set has B and C in it. And it can only download files from B and C because it does not know the existence of other peers in the network. So what would happen is A would send a request to B and C, checking if they have pieces with them, and B and C would respond, and A would keep track of the pieces available with the peers so that it would fetch and request the rarest piece that is there in the network. Right? It's like a greedy approach to fetch, to ensure that the file is distributed uniformly. Right? So let's talk about advantages of Rarest first, and then we'll go into the implementation part of it. So advantages, just from the core objective perspective, we can see the advantages of Rarest first being spreading the seed. So we are trying to, what would happen is, because we are prioritizing the rarest piece first to be downloaded by a peer, what would happen is we are reducing the dependency on the seeder. And we would only go to the seeder when someone is requesting the piece that is not existing in the network. So the load on the seeder is reduced. Whoever wants a piece that is not yet fetched by anyone in the network, then only would go to the seeder. Right? Otherwise, your network can internally distribute among themselves and can solve the problem. Right? Second, we would get an increased download speed, because the better the distribution of pieces in the network, the faster will be the download speed, because now it can go to multiple peers and basically download the pieces that it wants. Right? So you'd get a very fast download speed because there's a very nice uniform distribution of the pieces within the network. Third is enabling upload. We know that the reciprocation is a very important part of BitTorrent, through which it ensures that no one abuses or there are no free riders in the platform, right, or in the network. So what this would mean is, if you as a peer hold a rare piece, everyone in the network would want it from you. Because they want it from you, they would be unchoking you, giving you a better download speed. Reciprocation, right? And this is what makes this strategy very special, because now if you hold a rare piece, everyone wants it from you, so you'll in turn get a better download speed. So reciprocation, this is the core idea of choke algorithms anyway. We talked about choke algorithms in the previous video. If you have not dived deep, if you have not seen that video, please watch it, because it's a very superb algorithm that ensures there are no free riders and it solves such beautifully the entire problem. Right. So with reciprocation, we'll get faster download. So this is a good strategy of being rarest first is pretty solid here. And fourth and final and the most important one is preventing rarer piece missing, which means that we would never have we would never have a situation where a rare piece goes missing, because we are prioritizing downloading of the rare piece first, right? Which is really important, right? So reducing the dependency on the seeder while ensuring that even if someone leaves the network, we would still have the pieces floating around in the network that people can complete their corresponding downloads, right? Now we'll go into the implementation part of it. So now, how does a peer compute rarest piece? Okay, so this is where we would see how the overall flow happens. So every peer, like for example, peer A first went to the tracker to see who all are peers that it can talk to. And let's say the tracker sent peer B and peer C. So now what would happen is every peer has a peer set that it got from the tracker, right? Now there are two ways by which peer can tell about the pieces they have, because now what you need to know is, let's say I know the pieces, I know the peers, but how would I know what pieces they have? Someone has to tell me, but you cannot go to tracker, otherwise it would overburden the tracker. So it's the peers who would tell you the pieces they have, and there are two ways to do it. First is the have messages. So what happens is whenever a peer downloads a particular piece or it has a particular piece, it would broadcast a have message that I have this piece, right? So a series of have messages are sent by peers B and C for each piece that it has. So now A would be getting have messages from peers B and C. This way A can keep track of the pieces that B and C has on its own machine. And this is one way through which A would know the pieces that B and C has, right? The second way to do it is called bit-filled message. So when a connection is set up between two peers, right? Let's say peer A and peer B, after the initial handshake, what can happen is peer B can send a bit-filled message. A bit-filled message, basically very simple approach. What it holds, it holds for each piece, it has a bit in the bit field that is set to 0 and 1. 1 implies that the peer has this piece and 0 implies that it doesn't. So peer B, when the handshake is complete, peer B would have this bit field handy. It would know which pieces it holds. It would send this bit field to A. Once A gets the bit field, A would know the pieces that B has. And then now with this, one of these two approaches, A knows the pieces that the peer set of its has. What it can do is it can compute the rarest first, because it would know across its, and now here I'm talking about a very small scale of 3 nodes, but in reality it is 50 nodes. 50 nodes, and then and at max it goes to 50. But through this it would know the rarest piece, because it would know which all pieces does each of the peer in the network holds. And now what it can prioritize is it can prioritize downloading of the rarest piece, because it would know that, hey, this piece is the least that anyone has, so let me download that. So everyone tries to prioritize downloading of the rarest piece first, right? And the rarest piece is computed every time you receive a have message from a peer or you receive a bit-filled message from a peer, because you need to recompute it every time, right? So you would prioritize downloading of the rarest piece and it would be recomputed every time you receive a have message from a peer that something changed. Then you do a very quick recompute of it, right? Okay, so you would have foreseen that only rarest first is not enough to solve this problem, because there are lots of edge cases. Let's talk about those edge cases. First, when a peer has just joined the network, right, it would need to have downloaded the first piece as soon as possible. Why? Because P2P network works on reciprocation. If you have piece to give, you'll get a piece in return, right? So otherwise they are choked, right? This is what we've seen in the choke algorithm. So because of this, when a peer joins a network, it would not have any piece with it. Because if it does not have any piece, what would happen is it would need to prioritize downloading of first piece as soon as possible so that it has something to share. Now, if you go for a rarest first approach in this case, what happens is you would have to wait for a very long time for it to download. So this would slow down the overall download capacity, it would slow down the overall download rate of a particular peer who has just joined a network, giving it a poor experience. So what would you do? You would want to have a separate strategy for a peer that has just recently joined. So that is where random first policy comes in. So random pieces, because you are not applying any explicit logic over here, you are just downloading any piece that you can get at random from the network so that you have at least something to start with. So that is where if you have less than 4 pieces, exactly, if you have less than 4 pieces of a particular file that you are trying to download, then instead of going for rarest first, you would go for basically random piece strategy. Through this, what you would ensure is, you would ensure a very fast way to get at least some piece with you, so that you'll have something to share and then you'll get other pieces in return, right? So this is what you do when you have less than 4 pieces in total. But as soon as you hit 4 pieces, you would switch your strategy from random piece first to rarest first, right? So this is what you would use to ensure that you are, like, when you are just doing a cold start, when you're just starting up, you would not go for rarest first, but instead you would go for random first to have something to share with the network, right? So for the first 4 pieces, you would do random first and then you would switch to rarest first, right? Okay. Then comes a second policy, which is strict priority policy. Now, here, what I have been talking about is, you have a file in the network, it is broken into pieces, but piece is 1 MB big, for example, right? But a piece is also broken into blocks, and block is the unit of transmission. As in, when you are transmitting in one call, you'll get 1 block in return. You're not getting a piece in return, you'll get a block in return. Once you have all the blocks of the pieces, then you complete the piece and you say, hey, now I have this piece, right? Because piece can be big, block would definitely be small, which can be exchanged in one TCP call, right? So file is split into pieces and pieces are split into block. In each transfer, a block of a piece is transferred. And now things become interesting. So, given that a peer cannot contribute back to the network until it has a complete piece, because piece is a unit that we are operating at. Or a peer can say, okay, I have this piece, but to download a piece, it has to download multiple blocks. So what if a peer downloads 3 blocks from 3 different pieces? It would take a long time for it to complete one piece, right? So that is where what a strict piece policy or strict download policy says is that you would want to prioritize. So if you have downloaded a block of a particular piece, you should be prioritizing downloading of all the blocks of the piece, so that you would have a completion of a piece much quicker, so that you can contribute back to the network as soon as possible, right? So this way, or this policy would ensure that you are focused and you are downloading all the blocks of a piece, completing a piece, so that you can then broadcast a have message in the network and say, hey, I have this piece now, right? Very important. So this is how you would ensure that you are focused on downloading the piece on priority and as soon as possible. And the final policy is the endgame mode, right? So what it says is, the endgame mode is when you are about to finish the download. What would happen is, let's say you are downloading blocks, right? Because when you are downloading pieces/blocks, what might happen is, at the later stage of your download, at the final stage of your download, what would happen is, you might be needing, let's say, 5 blocks, and you have made request to all 5 of them. You have made request for all 5 of them, and now you are waiting for the response to come in. Now that you are waiting for the response to come in, typically towards the lag end of the download, things become slower because the pieces are hard to find, or because everyone else is anyway busy. So you would want to complete the download as soon as possible. So in order to do this, what happens is, when your download is about to finish, which means when you have made the request for all the blocks that you need, and now you are waiting for all of them to respond, what you do is, instead of that, you would make request to all the peers that you have. Instead of saying that, hey, I'll only talk to one peer to get my particular piece, you'll broadcast this to every peer in your peer set and say, hey, I need this block, give me all of them. right? So with this, what happens? With this, what happens is you are prioritizing completion of your download. And when this happens, you would say, ki, Arey, but now if I need a particular piece, let's say P1, and I'm sending it to all the peers that I need piece P1, what if all of them sends me that? It's okay. All of them would send you that. You would discard the redundant piece that you got, right? The piece that you got, you would basically create a file out of it. But then when all of them is about to send you that message, what you would do is, as soon as you receive a block in this endgame mode, when you receive a block, you would send a cancel message to everyone that, hey, I received this block, please don't send me again, to just try to minimize the network overhead that comes in. But you would say, ki, Arey, but requesting for all the pieces every time, basically it will be very taxing on the network. That it is taxing, but it is an end game mode, which means it would happen only at the end of the download, not in the middle of it. Given that, what we are doing is we are trading a little heavy on the network consumption versus faster download. We are always prioritizing faster download, right? And this is what is important to give a best download experience to a peer in the network, right? So just to iterate on the endgame mode is triggered when you wanted the last n blocks and you have made request for all of them. You would be broadcasting a message that, hey, I want all of these blocks, so that anyone who has it can prioritize sending it to you rather than you waiting for the response. And once you receive a block, you send a cancel message to everyone that, hey, I received this block, please don't send me. If you received in the middle, if you received a redundant block, you would discard it, right? This would make your overall download at the end much faster, right? You should not be doing it in the middle. You should only be doing in the end game, which means during the final stages of your download, you should be doing it to complete your download as soon as possible. And this is the piece selection algorithm that BitTorrent uses in order to ensure fault tolerance in the network while a very fast download speed or very fast distribution speed within the network. This is such a beautiful piece of algorithm. It's very intuitive and it's very simple to even write and build and code. And this is how your overall P2P network is built with Choke's algorithm to ensure you select the right peer and you and you basically penalize the free riders. And with Rarest piece first strategy, you ensure that you do not have any large dependency on seeder. And even if a node leaves, even if a seeder leaves the network, you would still have your network functional and the download would proceed as usual. So yeah, that's it for this video. This was the video on piece selection algorithm that BitTorrent uses. If you guys like this video, give this video a thumbs up. If you guys like the channel, give this channel a sub. This was the 5th video in the BitTorrent internal series, and I'll see you in the next one. Thanks again.